Okay, so for my project, I did the Königsberg Bridge problem. So basically, this was based off a city in former Prussia, which is now in Russia, and basically the geography of it was it had a river coming in, and then it split into two to go around an island, and then there was another passageway between the island, so it formed the island, and then it formed this other mainland here. And then they built 7 bridges, which are these green things here, so that people could get to other parts of the city conveniently. And the person that discovered this problem was Leonhard Euler, who was, as Hannah and Julie said earlier, was born on April 15, 1707 in Basel, Switzerland. And he was tutored by Johann Bernoulli, who was one of the Europe's best mathematicians of his time. And so, yeah. The problem was that Königsberg was a touristy location, so they were wondering, people were wondering if there was a way to cross every single bridge once and only once without doubling back, so without crossing a bridge twice. And here's an example of a failed attempt. So what Euler did, he realized that the only thing that was important in finding such a sequence would be the location of the bridges relative to the islands, meaning that the route within each landmass was irrelevant, because as long as you come in on a bridge and you exit a bridge, it doesn't matter what route you have inside the landmass as long as you go, come in and exit. So basically, you can simplify it down to this, where each point represents a landmass and each edge represents a bridge. So then he realized that for every vertex that was not a starting or ending point, there would have to be an even number of bridges going into that point, because when you go into a point, you'd have to also exit the point. Because if you just go in and you don't exit, then you have to stay there and you don't continue your travels. So for every point he found that for every point that was not the starting and ending point, it had to be even, so that half of them were used for coming into the node, and then half of them were used to going out. And so then he realized that if for a path to exist, the only thing that you would need to know would be the degree of the nodes, which means how many edges are going into that point. And so basically that means that the graph must have either 0 or 2 nodes of an odd degree. If there are 0 nodes, it is known as a Eulerian cycle, and it starts and ends on the same point. Because when you, for example in here, when A is the starting point, when you leave A, that's one path, then you come into it and out again, as mentioned before, so that's 3, and then you end in it with, obviously, so that makes 4. And then if you have 2 vertices of an odd degree, then it would be a Eulerian path, which is right there. And you'd have to start on one point with an odd degree, so like A, for example, and then end on C. Oh wait, here, Chris, go back. And then for this one, if you see that all 4 points have an odd degree, so then if you start in this one, for example, and you end in this one, then you would have one bridge between these 2 points that you do not cross without having to double back. So it is impossible to draw this with one continuous line. So then here, I pulled up the diagram from the previous slide, and as you can see, this island here has 5 bridges going to it, and all the rest of the landmasses have 3. So then that means that a Eulerian path is impossible, because there are not 0 or 2 nodes of an odd degree, meaning that there's no specific starting or ending point, so that one of the bridges will not be used. So then here's an example of a picture that can be drawn with one line, because the 2 blue points are the only 2 points that have an odd degree. So there is a way, I'm not going to show the way because it would take way too long, but there is a way to draw this picture with only one line. And there are also variations that have arisen from this problem, including what this looks like, a box, a rectangle with other rectangles inside of it. And basically there are 4 regions, each of these boxes, and then the outer region. And basically the goal is to find a line that goes through all the individual line segments once and only once without doubling back. And so these two both have 4. This is 5 and this is 7. So is the path. There is a path that exists, which is shown here, and it starts in either C or D and ends in the opposite one because they both have what would be considered as an odd degree of nodes. This one, where there are 2 rectangles on the top and 3 on the bottom, does not work, however, because there are 4 regions with an odd degree. So, like, this is an example of a failed attempt because these 2 segments do not get used at all. Okay, you could use that one, but you can't use that. So basically, this was the first theorem that was used in a new field of math called the graph theory and topology. And graph theory is basically it bases on like certain points and then the networks between those points. So certain examples are like the internet, because you have the points, which would be like each individual computer, and then the networks would be the connections between the computer. And then topology was also developed in this because it did not focus. The problem did not focus on the exact location of the bridges. It focused on the relative position of the bridges and the islands, like in comparing them to each other, not exactly where they were in the drawing.